Hey guys, alright, we've gotten through linear and quadratic equations, and it is time for us to start polynomial functions. Okay, you guys have learned about polynomials before. Let's talk about it one more time. This is the general form of a polynomial. The heck? What even is this? This is crazy, am I right? Okay, look. This is just saying x to the n is the degree of the polynomial function, and that can be anything. Okay, now linear equations, this is the linear term, all right, those are also polynomials. Quadratics are polynomials, but generally we refer to polynomials as things bigger than quadratics. So talking about x to the third, x to the fourth, x to the fifth, okay? And what happens is, like, let's say this is like x to the, I don't know, like seventh or something. Then every term could be represented x to the sixth, x to the fifth, x to the fourth, x to the third, x squared, x to the first. Okay, so those are polynomials. The exponents all have to be whole numbers. There's a few different words that you guys want to know. So it's degree. Okay, the degree is the highest exponent. And then the other thing you want to know is this coefficient in front of the highest exponent is called the leading coefficient. Okay, that's pretty important. All right. Now, when we talk about polynomials, just like with quadratics, all right, in polynomials, we're going to talk about multiple things. Okay, we're going to do this whole list. Leading coefficient test. Sometimes it's called, like, some people abbreviate it LCT, leading coefficient test to determine end behavior. You might be like, what the heck does that mean? We're going to talk about it. Guys, the leading coefficient test basically says which way the arrows go. Like if my polynomial goes like that or whatever. That's the leading coefficient test. We're going to talk all about it. For every polynomial, we're going to find x-intercepts. What are some other words for x-intercepts? Okay, x-intercepts are roots, zeros, solutions, right? And ultimately, it's where it crosses the x-axis. Okay, we can have multiple of those. And we're going to talk about a word that you may or may not have heard before. It's called multiplicity. It's a little bit tricky, but we're going to talk about that. All right, we're also going to talk about the y-intercept. The y-intercept is boring. It basically is just where it crosses the y-axis. Nothing super important about the y-intercept. It basically just gives you an extra point on the graph. Okay, we're going to talk about symmetry. There are two types of symmetry we're going to look at. Even and odd symmetry. One has y-axis symmetry. One has origin symmetry. We'll talk about all that. And then the maximum number of turning points. What the heck is a turning point? Well, a turning point is when I'm coming around, like picture, oh man, Colossus, right? You guys gone on Colossus, or like Twisted Colossus, I guess it is now. And that first drop where you get up to the top and then you're like, ah, holy crap. That's a turning point, okay? That's a turning point. When you get up to the top and you're about to drop. Or, gosh, even worse, what's that one, Goliath? Oh, my friends, have you been on Goliath? Goliath is the absolute worst. Because you go down and you go even under the ground and then you hit boom and you come back up under that. This is like the ground and Goliath goes under. Crazy. That's a turning point, okay? When you go down and come back up. So it's exactly what it sounds like. It's where it turns, all right? These are all things that are going to help us graph polynomials. So first, I'm going to talk about them, all right? So for each polynomial, we're going to find what's called the leading coefficient test to determine end behavior. Okay, so again, what the heck is end behavior? End behavior is which way the arrows go at the ends of the graph. All right? Now remember that n is odd, n is even. N stands for the degree. All right? And I kind of show you guys how this works. If I have an odd degree polynomial, okay, check this out. All right, my screen go up a little bit here. Here we go. Okay, if I have an odd degree polynomial. X to the third. Okay, let's make it an interesting one. Minus 5x squared plus 3x plus 4 or something. There we go. That is a lovely polynomial. Do you guys see a turning point right there? Right up there is a turning point. You guys see a turning point down there? You guys see some intercepts right there, some x-intercepts, some y-intercepts. Okay, I'm going to teach you how to find all that stuff. And I just made that question up right off the top of my head, too. All right. But, okay, which way do the arrows go? So you guys notice, yeah, you can see the dot down here. As I go down on this side, it goes to the left. It goes all the way down as I go. Up on this side, it goes to the right. Okay? This is an x to the third. All right? Again, while we're looking at this, just because it's a pretty good example, we'll bring some stuff up. There are 3 points right here, you guys. What are those points called? All right? Hopefully you guys chose that correctly. There are 2 points here. Okay? These are called turning points. All right, those are called turning points. There's a point right there. What point is that? What is that point called? Okay, these are all the things that are going to help us to graph this polynomial. And then again, we have which way the arrows are going. So when the degree is odd and that is greater than 0, that means positive. Now, what's a sub n? A sub n is the coefficient in front of here. So it's basically saying the x to the third, right? I mean, I could put a number there. I could put 2x to the third. It doesn't make my graph look a lot better, but whatever. Okay? It's a positive number. What happens is my arrows will go down to up. Okay? You kind of need to like memorize this, but I'll teach you a pretty easy way to do it. All right? The next one is what happens if this is negative? Let's go ahead and make it negative. In front of the x to the third, and see what happens. So when I make it negative, flips upside down. Kind of knew that it would do that. But look, on this side, the arrow goes up that way, and on this side, the arrow goes down that way. Okay, so I flipped it around, but my arrows are going to go up to down when I put a negative in front. So they go opposite, these arrows go opposite direction. Okay? All right. Next one. Let's say n is even. Say I take this and instead of, let me just get rid of that real quick. Instead of x to the third, let's say I make it x to the fourth. All right, cool. You guys see that graph? Now what do you notice about the arrows on that? On this side they go up. On this side they go up. All right, so they're going to go up on both sides. So if n is even, remember that's the degree, the highest exponent is even, and there's a positive in front of it, it goes up, up, okay? What happens if there's a negative in front of it? Let me go ahead and put a negative in front. What happens? We'll look at my arrows. This kind of looks like a parabola. It's not because it's an x to the fourth, but my arrows go down, down. All right. Okay, so they're going to go down, down. All right, you guys. Now, how do you remember this? Because you kind of have to like memorize this. How are you going to memorize this? Well, look, I think of the graphs that I know what they look like. We start with even because that's a little bit easier. Do you guys know what x squared looks like? Yeah, it's a parabola, right? Okay, my friends, check out my arrows right here. Up, up. And what happens when I have a negative parabola? We've been talking about that. It goes upside down. And what happens to my arrows right here? Down, down. They match. So I feel like that one is pretty easy because x squared, and then if it's x fourth, x sixth, x to the eighth, okay, the arrows are going to follow the same pattern. The other one over here is a little harder for me to remember, but you know which one I think of that's odd? I mean, you could do x, but the one I always think of is x to the third, okay? And I know x to the third, that's a cubic. I know it goes like that. That's one of the ones we like kind of usually like memorize or whatever. Look at the arrows on that though. It goes down, up, just like those arrows. And what happens when I flip it upside down? Negative x to the third. Okay, look at those arrows. So if you remember x to the third and x squared, it'll kind of help you remember which way the arrows go. My friends, that is the leading coefficient test. Now, you can always either draw the arrows, and like if I say, what's the leading coefficient test, and I want to state what it is, you can either draw the arrows, or you can say like down, up, up, down, up, down, down. You can do that. Or like falls, this is the like words they use like in your book, which we're not even using really. Falls left, rises right. Okay, so what would the next one be? The next one would be rises left, falls right. You can use those words, but I don't usually use that. This would be rises left, rises right, falls left, falls right. I usually just draw the arrows, okay? Or you say up, up, or down, down. All right, that's how you remember. Okay, cool. X-intercepts are also known as, you guys know this, we've talked about this a ton, solutions. Highlight that better. Here we go. Solutions, zeros, or roots. All right. Okay, check this out. If n is the degree, n will also equal the number of solutions. Always. Okay, if you have an x to the third polynomial, you will have 3 solutions. Okay, if you have an x to the 6th polynomial, you will have 6 solutions. For sure, 100%. You just will. Now, the thing that can be a little tricky with that, though, is that solutions can actually be real numbers that are either rational or irrational, or they can be imaginary. Okay, what's the difference? Let's talk about these words really quickly. Real means it's a number that you can see on a graph. All right, that's what real numbers are. Now, real numbers can be rational or irrational. A rational number would be like 5. Perfect. Or like a half. Those can be solutions. And you would see those on the number line. It would hit at 5, or it would hit at a half, or, you know, it hit at negative 6.4, or whatever. Those are rational. You can also have irrational solutions. With irrational, we're talking about things like square root of 10, or like 2 plus or minus square root 3. You know how when you're doing quadratic formula, you sometimes get that? Those are irrational functions. Okay, last but not least, we have imaginary. You cannot see these on a graph. And sometimes they look like this, like 2 plus or minus I. Okay, something like that. So check it out. All right, let's say that I have, let me make x to the third equation, okay? Just making something up. Minus 6x. I'm going to stop right there. That's actually a great equation. Okay, now look, guys. X to the third, right? That's an x to the third. How many solutions should I have? How many solutions? Okay, I have to have 3 solutions because it's an x to the third. Now, how many x-intercepts do I have? I'll actually put them on there for you so you can see how many x-intercepts do you see on this graph. Okay, 3 solutions, 3 x-intercepts. Perfect. All right, now I'm going to make this a little bit weirder. I'm going to go plus 2. Plus 4. There we go. All right. How many solutions is this going to have? It's an x to the third. How many solutions is this graph going to have? Okay, right, guys. It's going to have 3 solutions. It has to. But how many x-intercepts does it have? How many times does it cross the x-axis? it only crosses the x-axis one time. But we have to have 3 solutions, so how does that make sense? Well, I know that this is going to have 2 imaginary solutions. One solution is going to be there, and the imaginary ones won't show up. Okay? That's probably irrational. It looks like an irrational number. I don't know. Before we put that on there, look, these were like lovely rational numbers. Okay? But then you can always mess with these polynomials and make them have irrational or whatever. All right? So they could be real. They could be imaginary. That depends whether you see them on a graph or not. All right. Multiplicity, my friend. Okay. So whenever I would teach this lesson in person, in class, right? I'm going to show you guys something. All right. There is a movie. It was back in 1996. I know. It's a super old movie. Okay. Let me show you guys this picture real quick. And it was called Multiplicity. Okay. It had, what's his name? Michael Keaton. I'm pretty sure that's his name. Michael Keaton, right? The original Batman.
Adam West?
No, well, not, okay, fine, not the original Batman, but Michael Keaton, right? Wasn't he the original of the newer Batmans?
Yes.
All right, cool. Well, anyways, you guys check this out. So there's this movie called Multiplicity. I just did like a Google search. I'll show this to you. This is the like movie poster for it. Okay. Well, it's this guy, and he had all sorts of like, I don't even remember. He couldn't pay his rent or something, and he was like, "Gosh, if only I could clone myself." And so he cloned himself like a bunch of times. This was one of the like movie covers. Michael Keaton. I was right. Look at me. Okay. Michael Keaton. See, look, guys, it's funny, 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 funny. 4 times. That's funny with a multiplicity of 4. You're gonna hear me use the word multiplicity a lot. Every time I say the word multiplicity, I think of freaking Michael Keaton being duplicated a bunch of times. That is just what I think of. So let's talk about multiplicity. All right, you guys. So there's my little story on multiplicity. Here we go. Okay. Multiplicity of 1, 2, 3, or 4. Let's say I have a root. Let me use like x minus 5. Okay. Now x minus 5. If I have a multiplicity of 1, what it looks like is it crosses at 5. It's actually just a straight line. It just crosses like that. It crosses normal. All right. Let's see what happens when I do x minus 5 with a multiplicity of 2. So first of all, what does a multiplicity of 2 mean? Well, you can either write it 2 times or you can square it. Okay. So you can go x minus 5, x minus 5. You can write it twice or you can square it. Okay, so here we go. Let me show you on here. So this is if I do x minus 5 1 time. Okay. And let me just kind of fix my graph here for you guys. There we go. Perfect. All right. Whatever. There we go. Just wanted to go back to normal, darn it. Did you guys know if you're ever using decimals, you can go up to here and you can just kind of go like negative 10 to 10. Negative, let me delete all that. Negative 10 to 10. Okay. Kind of reset my graph. Anyway, there we go. Now, guys, when I have a multiplicity of 2, it means I have that same thing twice on x minus 5. Look at what happens at the 5. Do you guys see how it comes down and it bounces and it goes back up? Okay, it bounces at the 5. And it's actually the same way as if we just wrote x minus 5 squared, right? If there's 2 of them. Okay, so I'll put it right here. And what happens is, when you have a multiplicity of 2, so I'm going to introduce you some special words, bounces. All right, it bounces. When it goes 1 time, it crosses. So the difference between crossing and bouncing. Let's look at what happens when we make it a multiplicity of 3. Let me put another x minus 5 on there. Well, it crosses, but do you guys see how it doesn't just cross normal? it crosses with this weird little curvy cross, okay? It crosses, but it gets kind of like, it like kind of flattens out right there and then crosses. What does that look like? Well, it looks exactly like x to the third. That's the whole point. When you have a multiplicity of 3, you do what I call it like kind of a flat cross. That's kind of the best way I have to describe it, and it's like this. All right. So a flat cross would like kind of go in like that and go like that. So that's if I have 3 of these. Now instead of writing it 3 times, I can just do that, okay? That's be a flat cross. Let's say I have a multiplicity of 4. Multiplicity of 4, okay? Let's see. All right, let's come over here. Let's see what's going to happen. So I'm going to go ahead and put one more on there. All right. Now, it bounces again, but it bounces in a different way than when it was squared. Do you guys kind of see the difference? Let me like zoom in. This green line, when it's squared, it comes down, hits a 5, bounces back. Same thing on this blue line, okay? Except that it kind of flattens a little bit more. So what do you think would happen if I did it to the 6th? Well, that's my purple line. It flattens even more. So all of these are going to keep bouncing. They're just going to keep flattening even more and more. So a 4th, I would call it like a flatter bounce. Okay. And so it kind of like comes down like this. Let's see here. And it comes back up. It's not like, I mean, I didn't draw that very well, but you guys get the idea. It makes like a flatter bounce. All right? So that's what it looks like when you have multiple roots. Now, when I was saying, like, let's say it's a 3rd degree polynomial, you have to have 3 solutions. Well, sometimes your solutions are 5, 5, 5. 3 times the same number. They still count as different solutions. All right? All right, sweet. Here we go. Even and odd functions. You guys, there's a little typo right here. So if you did print these out, you want to fix this. Okay, an odd function is basically, you learned this in Algebra 2 trig, but it's a function where if I plug in a negative, it makes the answer negative. It has origin symmetry. An even function, it basically says if I plug in a negative, doesn't make a difference, it's still positive. What kind of graph could I plug in a negative number and get the same answer as when I plugged in a positive number? What kind of graph could I do that? Think about that real quick and see what you guys want to put. Okay, I can think of 2. Okay, I can think of 2. I can think of like x squared. Because what happens if I plug in a negative to that? Because like if I plug in 3, I get 9. But if I plug in negative 3, I also get 9. So a squared, or even like, you know, an x squared, something like that. Okay, anything else you guys can think of that has even symmetry? The other one I always think of is absolute value, right? So like, let's say I did, what's the absolute value of 2? What's the absolute value of negative 2? Also 2. So absolute value, I can put my absolute value like down here, but okay, these things have what we call y-axis symmetry. That means that if I fold it along that line, they will match up. Okay, check this out real quick. I'm going to make an equation up here with some symmetry. I'm going to say x to the 4th minus 5x squared plus 3. Check this out. Okay, this is an even function. You guys see that? If you were to fold that, let's make this a different color, make it more pretty. There we go. If you were to fold that right along the middle, do you guys see how it would match up? Now, why is this even? Well, because x to the fourth, that's an even exponent. X squared, that's even. And this is technically an even exponent because guess what? It's x to the 0. Okay? So see how it's like 4, 2, 0? So anything that has an exponent of like x to the fourth, x squared, constants, because constants are x to the 0. Okay? Those can combine to make even functions. X to the 6th. You get the idea. Now, there are other even functions. Like I pointed out, absolute value is an even function. If I remember correctly, like cosine of x is an even function. Okay, there are other even functions. All right, let's go ahead and look at an odd function now. An odd function would be something where if you plug in a negative, you get a negative. I mean, there's a lot of things that do that, but you get the same negative that you plugged in. So maybe like x to the third, right? Because if I plug in negative, okay, let's do it this way. If I plug in 2, I get 8. If I plug in negative 2, I get negative 8. So it has this like kind of symmetry. Here's another graph that I'm going to go ahead and draw for you. I don't know what the equation is, but something like that. Okay, you guys, so this has what's called origin symmetry. It's like the highest that point goes, there's a matching one down there. It's like that point up there, there's a matching one down there. And it's symmetric about the origin. Let me come back and take this equation real quick. And instead of 4, 2, 0, let's put some odd exponents in there. Okay? Instead of 4, 2, 0, let's put, hang on here, 5, 3, and 1. Woohoo! Check it out. That's a very cool graph. That is a graph that has origin symmetry. Look, whatever point that is down there, the opposite is down there. Whatever point that is down there, the opposite is up there. That is a nice origin symmetry. It's almost like you have to fold it a couple times to get it there. Origin symmetry. Okay. Odd functions have, summarize this here for you, origin symmetry. Even functions have y-axis symmetry. Okay, makes sense? The last thing I'm going to tell you is about turning points. Whatever polynomial has a degree n, it can have at most n minus 1 turning points. Let's take a look. This is a 5th degree polynomial. Okay, 5th degree polynomial. Now, my arrows go down, up, okay? Remember, turning points are like you're on a roller coaster. You're going up, you hit the top of the roller coaster, you go back down. That's a turning point. You hit the bottom, you go back up. That's a turning point. You guys see turning points here? 1, 2, 3, 4. Okay? It's a 5th degree polynomial. It has 5 turning points. That's how many it can have at most. It can have 1 less than what it started with, okay? So if I get back to what I had before, which was a 4th degree polynomial, that was 2, and that was 0. What is the most number of turning points it can have? Is a 4th degree polynomial. It can have 3. 1, 2, 3. It has 3 turning points. So it's always n minus 1. Okay? So let's say I had a 7th degree polynomial. I shouldn't put n, I should put x. Sorry. X to the 7th. How many turning points could that have? What's the most number of turning points that could have? All right, so hopefully, guys, you said it has max 6 turning points. All right. Okay, awesome. So hopefully that makes sense, and then next time we'll go ahead and go over some actual like example problems and stuff, okay? All right, sweet. There you go.